snap your fingers. In the time it took for that sound to leave your hand and reach your ear, a beam of light could have circled the Earth 7 times. 7 times, in a fraction of a second. To a biological creature like you or me, the speed of light, 299,792,458 meters per second, is indistinguishable from magic. It is instant. It is the speed of a thought. It is the ultimate limit of our reality. For centuries, humanity has worshipped this speed. We view it as the golden standard. We build our cables, our processors, and our dreams of interstellar travel around it. We look at the stars and think, if only we could go that fast, the universe would be ours. But this is a lie. We are about to embark on a journey that will dismantle your perception of speed. We are going to prove that on the scale of the cosmos, the speed of light is not fast. It is agonizingly, tragically, terrifyingly slow. It is a snail crawling across a continent. And the light year, the distance light travels in 1 year, is not a unit of measurement for explorers. It is the thickness of the prison walls that surround us. Let us begin by looking at our own backyard, the solar system. We usually think of the sun as being right there. It dominates our sky. It warms our skin. It feels immediate. But it isn't. The light hitting your eyes right now left the surface of the sun 8 minutes and 20 seconds ago. You are not seeing the Sunday. You are seeing a ghost of the Sunday. You are seeing where the sun was. If the sun were to suddenly vanish, if it were simply deleted from reality this instant, you would not know. For 8 minutes and 20 seconds, the sky would remain blue. The flowers would continue to photosynthesize. The gravity would still hold the Earth in orbit. You would finish your coffee. You would kiss your child. You would worry about your taxes. We would be living in a solar system that no longer exists. We would be orbiting a phantom. And then, suddenly, the darkness would arrive. The gravity would snap, and we would be flung into the void. This 8-minute gap is the first crack in our reality. It is the first hint that we are disconnected from the now. But 8 minutes is nothing. We can handle 8 minutes. It's a coffee break. Let's move out. Let's go to Mars. Mars is our dream. We want to colonize it. We want to be a multi-planetary species. We imagine grand cities and internet connections spanning the void. But we forget the lag. At its closest approach, Mars is about 3 light minutes away. At its farthest, it is over 22 light minutes away. Imagine you are an astronaut on Mars. Something goes wrong. A seal breaks. An alarm screams. You shout into your radio, "Houston, we have a problem." Your voice travels at the speed of light, the fastest thing in the universe. It screams across the vacuum. It takes 20 minutes to reach Earth. In Houston, the flight controller is drinking coffee. He hears your scream 20 minutes after you screamed it. He immediately hits the button. "We read you. Mars. Fix the seal." That message takes another 20 minutes to get back to you. 40 minutes have passed. You are already dead. The speed of light killed you. This is the reality of space travel that science fiction ignores. There is no conversation in space. There is only history. Every message sent is a message in a bottle, thrown into a black ocean, hoping someone finds it years later. To conquer the solar system, we must accept that we will never truly speak to each other again. We will only leave voicemails. Now, look at Voyager 1. It is the fastest object humans have ever built. It has been flying for nearly 50 years. It is traveling at 61,000 kilometers per hour. It has left the planets behind. It is in the interstellar dark, but in terms of light speed, it is pathetic. Voyager 1 is only about 22 light hours away. It hasn't even reached a single light day. And the edge of our solar system, the Oort cloud, extends out to 1 light year. Think about that scale. Light, the fastest thing in God's creation, takes an entire year just to leave our own driveway. If you turned on a flashlight on Earth and aimed it at the edge of the Oort cloud, You would have to wait a full year for the beam to exit our system. And beyond that lies the abyss. The true void, the nearest star, Proxima Centauri, is 4.24 light-years away. If the Sun were the size of a grain of sand, Earth would be a microscopic speck of dust 3 centimeters away. On this scale, Proxima Centauri is another grain of sand 30 kilometers away, and in between those 2 grains of sand, there is absolutely nothing. Just 30 kilometers of empty, howling void. To travel that distance using our fastest chemical rockets, like Voyager, would not take a year. It would not take a decade. It would take 73,000 years. Civilization has only existed for 10,000 years. If we launched a ship to the nearest star when the first humans were painting in caves, that ship would still be traveling today. It would only be a fraction of the way there. The people on board would have forgotten Earth. They would have forgotten why they left. They would be a distinct species, evolved to live in a metal can, floating in the dark. We are not explorers. We are islanders. And we have just realized that the ocean is too wide to swim. We have looked at the street where we live, the solar system. We have looked at the neighbor next door, Proxima Centauri. Now, let us look at the city. The Milky Way galaxy. We see pictures of it in textbooks. A majestic, glowing spiral of 100 billion stars. It looks cohesive. It looks like a single object spinning in the dark. But this image is a deception. The Milky Way is not a place. It is a timeline. The galaxy is approximately 100,000 light-years across. Let's try to visualize this distance. Let's do a thought experiment. Imagine you are immortal. Imagine you can strip away your physical body and become a being of pure light. You decide to travel from one edge of the galaxy to the other. You start at the rim. You fly at the maximum speed limit of the universe, 300,000 kilometers per second. You fly. After 10,000 years, entire civilizations on Earth have risen and fallen. The pyramids have turned to dust. The ice caps have melted and frozen again. You are still just in the suburbs of the galaxy. After 50,000 years, the human species has evolved into something unrecognizable, or perhaps gone extinct. You are only halfway to the center. After 100,000 years, you finally reach the other side. The journey took you 100 millennia, and you were moving as fast as physics allows. Now, turn around. Look back at Earth from the other side of the galaxy. What do you see? Do you see the cities of the future? Do you see the ruins of New York or Tokyo? No, you see the light that left Earth 100,000 years ago. You see a planet of ice and wilderness. You see early hominids, Homo sapiens, just beginning to migrate out of Africa, huddled in caves, striking flint to make fire, afraid of the dark. You do not see us, you see our ancestors. This is the time machine effect of the light year. When we look up at the night sky, we are not seeing the universe as it is. We are seeing a museum. Look at the bright star Betelgeuse in the constellation Orion. It is a red supergiant destined to explode. It is 640 light-years away. If Betelgeuse explodes tonight, if it goes supernova and lights up the sky, we won't know. We won't know for 640 years. For 6 centuries, we will continue to look up at a star that is already dead. We will write poems about it. We will use it for navigation. We will teach our children to find it. We are admiring a corpse, and this applies to every single point of light in the sky. The farther you look, the deeper into the graveyard you go. Some of the stars you see tonight may have burned out 1,000,000 years ago, but their light is still traveling, carrying the image of a ghost across the void. This creates a profound sense of isolation. We usually think of the present as a universal concept. We think that now is happening everywhere at once, but in a universe defined by light speed, there is no such thing as a galactic now. We are disconnected from the reality of our own galaxy. Physics tells us that nothing can influence anything else faster than light. This is called causality. This means that if a civilization on the other side of the Milky Way destroys itself today, the gravitational waves, the light, the radio screams, will not reach us for 100,000 years. For 100,000 years, to us, they are still alive. Their destruction has physically happened, but causally, it hasn't. We are locked in a bubble of ignorance. The Milky Way is not a unified city where we can trade and talk. It is a collection of 100 billion lonely islands, separated by oceans of time so vast that no bridge can cross them. If we send a message to a civilization 1,000 light-years away, asking, "Are you there?" we have to wait 1,000 years for the message to arrive. And they have to wait 1,000 years for their answer to return. A simple conversation, "Hello," "Hi," takes 2,000 years. In that time, the civilization that sent the message might have forgotten they sent it, or they might have wiped themselves out. Communication implies exchange, but at these scales, there is no exchange. There is only archaeology. We are not talking to each other. We are leaving graffiti on a wall, hoping someone reads it long after we are gone. And remember, the Milky Way is just our galaxy. It is just one spiral in a sea of billions. If the distance across the Milky Way breaks our brains, wait until we look at the empty space between the galaxies, because out there, the light isn't just slow. Out there, the light is fighting a losing battle against the expansion of space itself. We have stood on the shores of our own island, the Milky Way. We have realized that even at the speed of light, it takes 100,000 years to cross it. But the Milky Way is just one island. If you look at the constellation Andromeda in a dark sky, you can see a faint, fuzzy smudge. It looks like a small cloud. That is the Andromeda Galaxy, a city of 1 trillion stars. It is our nearest major neighbor, and it is 2.5 million light-years away. Let that number sink in. 2.5 million years. When the light hitting your eyes tonight left Andromeda, human beings did not exist. There was no language. There was no fire. There were only primitive hominids, wandering the savannas of Africa. That light has been traveling through the void for the entire duration of human evolution. It traveled while the ice ages came and went. It traveled while empires rose and fell. It traveled while you were born, lived, and looked up. And it only just arrived. If there is a civilization in Andromeda looking at us right now, they do not see the Great Wall of China. They do not see our city lights. They see a green, silent earth. They see a world of animals. To them, we are not here. The gap between the galaxies is the true, deep dark. Inside a galaxy, the average distance between stars is about 4 or 5 light-years. It is vast, but it is manageable. But the space between galaxies? If the Sun were a grain of sand, and Proxima Centauri were 30 kilometers away, Andromeda would be on the other side of the planet. And in between, there is almost nothing. Just a few stray atoms, a freezing, absolute vacuum. To cross this void at the speed of light would take 2.5 million years. To cross it with our fastest current technology would take billions of years, longer than the Earth has left to live. We often dream of intergalactic travel. Science fiction shows us hopping from galaxy to galaxy like we hop from island to island in Hawaii. But the physics of the speed of light makes this a fantasy. Unless we find a way to break the laws of physics, we will never, ever leave the local group. We are confined to our archipelago, but it gets worse. The universe is not just empty space, it is structured. Galaxies cluster together. Our Milky Way and Andromeda are part of the local group. But if you zoom out, the local group is just a speck in the Virgo supercluster. And the Virgo supercluster is just a tiny limb of Laniakea. Laniakea is a web of 100,000 galaxies. It stretches for 520 million light-years. To send a message from one side of Laniakea to the other takes 500 million years. By the time the message arrives, the civilization that sent it will have evolved, died, and their star will have burned out. The biology that sent the message will likely be extinct. The speed of light turns the universe into a place where connection is impossible. We are not living in a community. We are living in a simulation of isolation. And this leads us to a terrifying question. If the universe is so big and light is so slow, are we seeing the whole picture? Or are we trapped in a bubble of visibility? Imagine you are in a thick fog. You can only see 10 meters in front of you. You know the world is bigger than 10 meters, but you cannot prove it. The observable universe is our fog. Because the universe has a beginning, the Big Bang, 13.8 billion years ago, light has only had 13.8 billion years to travel. If there is a star 14 billion light years away, its light hasn't reached us yet. We are blind to it. We are sitting in the center of a sphere of light. Everything outside that sphere is darkness. It is the unknown country. And every day, the sphere gets a little bigger. Every day, new light reaches us from slightly further away. But we are not winning this race, because while the light is trying to reach us, the road itself is getting longer. The prison is expanding. We have established that light is slow. But there is another player in this game: space. For a long time, we thought space was static, a stage where the stars danced. But in 1929, Edwin Hubble discovered the horror. Space is not static, it is stretching. Imagine the universe is a rubber sheet. The galaxies are glued to it. If you stretch the sheet, the galaxies move away from each other, but they aren't moving through space. The space between them is being created. This changes everything about the prison of speed. Imagine an ant walking on a rubber band. The ant walks at a constant speed, the speed of light. The destination is a crumb at the other end. If the rubber band is stationary, the ant eventually reaches the crumb. It might take a long time, but it gets there. But now, imagine someone is stretching the rubber band. The ant keeps walking, but the road ahead of it keeps getting longer. If the stretching is slow, the ant will still make it. But if the stretching is fast enough, the ant will make no progress. It will walk forever. It will die on the rubber band, never reaching the crumb. This is exactly what is happening to light in our universe. The space between the galaxies is expanding. For nearby galaxies, like Andromeda, gravity is strong enough to overcome the expansion. We are actually falling towards Andromeda. But for distant galaxies, the expansion wins. There are galaxies we see today that are moving away from us. And the farther away they are, the faster they move. This is Hubble's law. There comes a point, a specific distance, where the space is expanding faster than the speed of light. Wait, didn't we say nothing can travel faster than light? Matter cannot move through space faster than light, but space itself has no speed limit. Space can expand at any speed it wants. This creates a cosmic horizon. There are galaxies out there that are emitting light right now. That light is flying towards Earth at 300,000 kilometers per second. It is trying its hardest to reach us, but the space in front of it is expanding faster than 300,000 kilometers per second. The light is like a swimmer trying to swim upstream against a raging river. The swimmer is moving, but the river is faster. The swimmer is actually moving backwards relative to the shore. That light will never reach us. Never. No matter how long we wait, no matter how powerful our telescopes become, that light is trapped in a region of space that is causally disconnected from us forever. We are cut off, and because the expansion is accelerating, dark energy, the river is getting faster. This means that, over time, more and more galaxies are pushed across the horizon. Right now, we can see billions of galaxies. But in the far future, billions of years from now, the expansion will be so fast that all the other galaxies will have drifted beyond the horizon. Future astronomers born on Earth, or whatever planet we live on, will look up and they will see nothing. They will see the stars of our own galaxy. But beyond that, just empty, black darkness. They will think the Milky Way is the entire universe. They will have no evidence of the Big Bang, no evidence of expansion, no evidence of other civilizations. They will be alone in the dark, and our records, our photos of the Hubble Deep Field, will be considered myths, ancient legends of a time when the sky was full of islands. The speed of light, combined with the expansion of space, creates a trap. It tells us that we live in a golden age of astronomy. We are the only generation that can see the truth. We can see the galaxies running away. We can see the prison walls closing in, but we cannot stop them. We are watching the doors lock. Let's put a number on the tragedy. We talk about the observable universe, the sphere of things we can theoretically see. It is about 93 billion light-years across, but observable does not mean reachable. Just because you can see a mountain in the distance doesn't mean you can climb it, especially if the ground between you and the mountain is turning into a treadmill moving backwards at 1,000,000 miles an hour. Scientists have calculated the reachable universe. If we built a spaceship today, a spaceship capable of traveling at 99.999% the speed of light, and we left Earth right now, where could we go? Could we reach the edge of the map? No, because of the expansion of space. Part 4. Most of the galaxies we can see in our telescopes are already gone. They have already crossed the point of no return. Calculations suggest that 94% of the galaxies in the observable universe are permanently beyond our reach. 94%, even if we were immortal. Even if we had godlike technology, even if we traveled at the speed of light, we could never reach them. We can still see their old light arriving, the ghost of their past. But the physical galaxies are gone. They have been carried away by the expanding flow of space, moving faster than we can ever chase them. We are effectively restricted to a tiny pocket of the cosmos, just 6% of what we can see, and that number is shrinking every second. Every second that passes, another star slips over the horizon. Another world becomes unreachable. Another civilization is cut off from us forever. The universe is deleting files. This is the true horror of the speed of light limit. It's not just that it makes travel slow, it's that it makes the universe finite. We grow up believing the possibilities are endless. The sky is the limit. But the limit is real, and it is much closer than we thought. So, what does this mean for us? It means that interstellar empires, like in Star Wars or Dune, are likely impossible on a large scale. You cannot run an empire if a message from the capital takes 100,000 years to reach the border. By the time the order arrives, the war is over, the emperor is dead, and the language has changed. The speed of light forces localization. It forces civilizations to stay small, to stay in their own solar systems. Maybe, at best, a small cluster of nearby stars. It creates a universe of isolated city-states, separated by vast, unbridgeable deserts. We are not going to conquer the galaxy. We are going to tend our own garden, because the garden is all we have. But is there a way out? Is the speed of light truly the ultimate law? Or is it just a local ordinance? Throughout history, we have found barriers that seemed impossible to break. The sound barrier, the gravity of Earth. We broke them. Are we looking at the speed of light the wrong way? We have been treating space as a distance to be crossed, like running a race. But what if we don't run? What if we fold the track? In the next part, we will stop looking at the speedometer and start looking at the geometry. We will ask, can we cheat? Can we bend the bars of the cage? We need to talk about warp drives. We are trapped. We have established that conventional travel is impossible. We cannot push a ship to the speed of light. As Einstein proved, as you approach light speed, your mass becomes infinite, and the energy required to push you becomes infinite. The universe has a no trespassing sign written in the math of relativity. But Einstein also gave us a loophole. Special relativity says matter cannot travel faster than light through space. But general relativity says space itself can do whatever it wants. Space can expand faster than light, as we saw in Part 4. Space can stretch. Space can contract. So, in 1994, a Mexican physicist named Miguel Alcubierre asked a dangerous question. What if we don't move the ship? What if we move the space around the ship? Imagine you are standing on a moving sidewalk at an airport. You are standing still, but the floor is moving, carrying you forward. The Alcubierre drive, or as science fiction calls it, the warp drive, works on this principle. It proposes building a ring around a spaceship. Inside the ring, space is flat and normal. The astronauts feel 0 G. They drink their coffee. Time passes normally. But the ring does something violent to the outside world. In front of the ship, the ring contracts space. It crunches the kilometers down, making the distance shorter. Behind the ship, the ring expands space. It stretches the distance out. You are effectively surfing a wave of space-time. The ship sits in a warp bubble. The bubble moves through the universe faster than light, but the ship inside the bubble never moves faster than light locally. It is the perfect crime. We are not breaking the speed limit. We are shortening the road. If we could build this, the prison walls would shatter. We could reach Proxima Centauri in days, not years. We could cross the galaxy in months. We could outrun the expansion of the universe. We could catch the galaxies that are fleeing from us. But there is a catch. There is always a catch. To bend space-time like this requires gravity, massive gravity. To contract space in front of you, you need the mass of a planet. But to expand space behind you, you need something that doesn't exist in our grocery stores. You need negative energy. Gravity attracts. Mass attracts. That pulls space together. To push space apart, you need anti-gravity. You need a substance with negative mass. We have never found negative mass. It might not exist. And the energy requirements? When Alcubierre first did the math, he calculated that to create a warp bubble just 100 meters wide, you would need more energy than exists in the entire observable universe. It was impossible, but over the years, we have refined the math. We have optimized the shape of the bubble. Recent calculations suggest we might only need the energy equivalent of the planet Jupiter. That is still a lot, but it is not infinite. It brings the warp drive down from impossible to merely extremely difficult. But there is a darker problem with the warp drive, one that NASA doesn't like to talk about: the sterilization. As the ship flies through space inside its bubble, it is sweeping up particles, dust, hydrogen atoms, radiation. These particles get trapped in the warp space in front of the ship. They build up, they get energized. When the ship arrives at its destination, when the bubble is turned off, all that trapped energy is released in a single instant. It would be a beam of high-energy gamma rays and particles blasted directly at the planet you are visiting. You wouldn't just be arriving, you would be arriving with a death ray. You might wipe out the very civilization you came to greet. The Alcubierre drive turns a spaceship into a weapon of mass destruction. So, surfing space might be too dangerous. But maybe we don't need to surf. Maybe we don't need to cross the distance at all. Maybe we can go under it. If you take a sheet of paper and draw 2 dots on it, point A and point B, the shortest distance between them is a straight line. But if you want to get from A to B instantly, you don't draw a line. You pick up the paper, you fold it, you make A touch B, you punch a pencil through. This is the classic explanation of a wormhole. It is the Einstein-Rosen bridge. Albert Einstein and Nathan Rosen realized in 1935 that the math of black holes allows for a tunnel. A black hole bends space-time down to a singularity, a bottomless pit. But if you connect that pit to another pit somewhere else, you create a throat, a shortcut. You could enter a wormhole near Earth, take a few steps, and emerge near Andromeda, 2.5 million light-years away. You haven't traveled faster than light. You have traveled a shorter distance through a higher dimension, the bulk. This is the ultimate dream of escape. No travel time, no aging, no isolation. The universe becomes a subway system, but the universe hates shortcuts. Every time we try to model a wormhole in physics, it fights back. First, natural wormholes seem to be microscopic, smaller than an atom, quantum foam. To send a human through, we would need to grab one and inflate it to the size of a city. Second, they are unstable. Gravity wants to crush the tunnel. As soon as you try to step inside, the throat collapses. It pinches off. You are crushed into a singularity. You die. To keep the door open, you need a doorstop. You need that same mysterious substance we discussed with the warp drive. Exotic matter with negative energy density. You need to coat the throat of the wormhole with anti-gravity to push the walls apart and keep them from collapsing on your ship. But let's assume we can do it. Let's assume we find the exotic matter. There is a third problem: feedback. Imagine you have a microphone and a speaker. If you put them too close together, you get a screeching noise, a loop. A wormhole connects 2 points in space. But radiation, light, can travel through it. Light could enter the wormhole, travel to the other side, loop back through normal space, enter the wormhole again, over and over. Because the wormhole is a shortcut, the light can loop infinitely fast. The energy builds up instantly. The wormhole becomes a laser beam of infinite intensity. It vaporizes itself before you can even turn the key. So, wormholes might be self-destructing bridges, but there is an even stranger possibility. Maybe wormholes are already here. We usually think of black holes as dead ends, but we have never looked inside one. Some physicists suggest that the supermassive black holes at the centers of galaxies are not holes. They are the mouths of wormholes connecting to other universes or other times. What if the dark matter web that connects the universe is actually a network of microscopic wormholes? What if the universe is already riddled with tunnels, but we are too big to fit through them? We are giants trying to crawl through the eye of a needle. But even if we solve the engineering, even if we build the warp drive or open the wormhole, we run into the final boss, the ultimate guardian of the prison. If you can travel faster than light, you break the order of cause and effect. You break time. Here is the truth that science fiction hides from you. Faster than light, FTL, travel, is time travel. You cannot have one without the other. They are geometrically the same thing. In special relativity, time is relative. Now depends on your speed. If you move fast, time slows down for you. If you move at the speed of light, time stops. If you move faster than light, logically, mathematically, time runs backward. Let me give you a scenario. Imagine you have a warp ship. You can travel instantly. You are on Earth. You have a friend on a planet 10 light years away. You look through your telescope. You see your friend as he was 10 years ago because of the light delay. You jump in your warp ship. You fly instantly to his planet. Now you are standing next to him. You shake his hand. But then, you turn your telescope back toward Earth. You look at yourself. Since you traveled faster than light, you have outrun your own image. You look through the telescope and you see yourself 10 years ago on Earth. You are looking at your past self. Now, imagine you jump back to Earth instantly, but you use a trajectory that exploits the relativity of simultaneity, a complex relativistic effect. The math says you can arrive on Earth before you left. You could arrive yesterday. You could walk up to your past self and stop him from getting on the ship. This creates a paradox. The grandfather paradox. If you stop yourself from leaving, then you never went to the planet, so you never came back. So you never stopped yourself, so you did go. Reality breaks. The universe cannot handle contradictions. Cause must come before effect. The glass must fall before it shatters. If FTL travel allows you to shatter the glass before you drop it, then the universe makes no sense. History has no meaning. Stephen Hawking proposed the chronology protection conjecture. He believed that the laws of physics are rigged to prevent time travel. He believed that whenever you try to build a time machine, or a warp drive, or a wormhole, something will always go wrong. The feedback loop will destroy the wormhole, the negative energy will fail, the vacuum will collapse. The universe protects itself. It protects history. And the price of protecting history is the prison. The speed of light limit exists to preserve the timeline. It exists to stop us from messing up the past. We are locked in our cells, separated by light years, not because the universe is cruel, but because the universe is safe. If we could zip around instantly, we would create chaos. We would rewrite reality. So, the walls are high. The gaps are wide. We are allowed to look at the other islands, but we are not allowed to touch them, because if we touch them, we might break the story. So, where does that leave us? No warp drive? No wormholes? Are we truly stuck here forever? Are we destined to die on this rock, or maybe Mars, and never see the stars up close? Perhaps not. We cannot go faster than light. We cannot cheat time, but we can cheat death. If we cannot shorten the journey, we must lengthen the life. We need to stop thinking about speed. We need to start thinking about endurance. We need to talk about the generation ship. If we cannot cheat the distance, we must endure it. If Proxima Centauri is 73,000 years away, no human being can make the trip in a single lifetime. So, we build an ark, a massive, spinning cylinder, a world inside a bottle. We fill it with forests, lakes, and cities. We launch it into the dark, powered by nuclear fusion, slowly accelerating to a fraction of light speed. The first generation, the crew who launch from Earth, are heroes. They are pioneers. They remember the blue sky. They remember the smell of rain on asphalt. They have a mission. They accept their sacrifice. But they will die long before the ship reaches the halfway point. Then comes the second generation, and the third, and the 50th, and the 1000th. These are the middle children. They are born in a metal hallway. They have never seen the sun. They have never felt wind that wasn't recycled by a fan. They have never stood on a planet. To them, Earth is just a story, a myth told by the elders, a blurry blue dot in the telescope that gets smaller every year. And Proxima Centauri, the destination? It is also a myth. It is a star that will not be reached for another 50,000 years. The middle children did not choose this mission. They were conscripted by their ancestors. They are prisoners of a dream they did not dream. Their entire universe is the ship. Sociologists predict that on a generation ship, society would mutate. Language would drift. In just a few centuries, the English or Mandarin spoken by the founders would evolve into a new, incomprehensible dialect. The technical manuals for fixing the engines might become holy texts, recited but not understood. The mission would become a religion. We travel to the promised land, but what happens when faith breaks? What happens in year 10,000, when a generation decides they don't care about a planet they will never see? What happens when they decide to turn the ship around? Or worse, what happens when they forget? Information degradation is inevitable. Hard drives rot, paper crumbles. After 20,000 years, the inhabitants of the ship might forget they are on a ship at all. They might believe the metal walls are the boundaries of the universe. They might believe the engine hum is the voice of God. They would be a tribe of savages living inside a high-tech starship, drifting through the void, completely unaware that they are going somewhere. And when the ship finally arrives at Proxima Centauri, 73,000 years later, who will step off? Will they be scientists ready to explore? Or will they be terrified primitives, blinded by the light of a real sun, worshipping the ground they walk on? The generation ship solves the problem of distance, but it creates a tragedy of culture. It ensures that the humanity that arrives is not the humanity that left. But there is another way, a way to skip the middle. We stop the clock. The alternative to the generation ship is the tomb. If we don't want to sentence thousands of generations to life imprisonment in the void, we must put the crew to sleep. Suspended animation, hibernation, cryosleep. We see it in nature. The wood frog freezes solid in winter. Its heart stops. Its blood turns to slush. It is dead, for all practical purposes. And then, when the spring thaw comes, it wakes up and hops away. We want to do this to humans. We want to replace the blood with antifreeze. We want to lower the body temperature until metabolic time stands still. If we can do this, the 73,000-year journey becomes an instant. You close your eyes at Earth. You open them at Proxima Centauri. For the astronaut, the prison of speed vanishes. But for the ship, time continues to march. Imagine the risk. You are asleep. You are helpless. You are locked in a pod, trusting a computer to watch over you for 70 millennia. 70,000 years is a long time for a machine. Metals fatigue. Circuits degrade. Cosmic rays pierce the hull, flipping bits in the computer's memory. A bit flip. A single zero becomes a 1. Maybe that bit controlled the temperature of your pod. Maybe it controlled the navigation. While you sleep, the AI might go insane. It might forget who you are. It might decide to turn off the life support to save power. Or you might simply drift. What if the engines fail in year 5000? The ship stops accelerating. It just drifts. You sleep on 10,000 years, 50,000 years, a million years. You become a capsule of frozen meat, drifting through the galaxy forever. A silent monument to a failed species. But let's assume it works. Let's assume you wake up, the lid opens, you gasp the air, you look out the window, you see the alien sun. You made it. But what happened back home? While you slept for 73,000 years, Earth continued to spin, civilizations rose and fell, wars were fought, maybe an asteroid hit, maybe humanity went extinct, or maybe science moved on. This is the weight calculation paradox. If you launch a slow ship today, in 100 years, we might invent a fast ship. That fast ship would launch, overtake you, and arrive at the destination thousands of years before you. When you finally wake up, looking for a pristine new world, you might find a bustling civilization waiting for you. They might look at your ship as a relic, a museum piece. Look, here come the cavemen in their frozen canoe. You sacrificed your life. You left everyone you loved. You slept for eons, only to arrive and find out you were obsolete the moment you left. The long sleep saves your body, but it severs your connection to time. You become an immigrant from the past, arriving in a future that doesn't need you. And there is one final horror. The human body was evolved for Earth. 1G gravity, 24-hour days, magnetic fields. Space is different, and if we live in space long enough, we will stop being human. Biology is plastic. It molds itself to the environment. On Earth, we have thick bones to fight gravity. We have dark skin to fight the sun. We have eyes adapted to the atmosphere. But in the void, the rules change. If we live on a generation ship or a colony on a low-gravity moon for thousands of years, natural selection will take over. First, the skeleton. Without the crushing weight of Earth's gravity, heavy bones are a waste of energy. The humans of the deep dark will become tall, elongated, thin. Their bones will be like bird bones. If they ever return to Earth, the gravity would crush them instantly. They are exiled from their homeworld by their own biology. Next, the fluids. In 0G, fluids shift to the head. The face becomes puffy. The legs become spindly. Next, the eyes. Inside a spaceship, or under the dim light of a red dwarf star like Proxima Centauri, you don't need protection from the sun. You need to gather light. Their eyes might grow huge, like the eyes of deep-sea fish. Their pupils would be massive black pools. Their skin, protected from UV radiation by metal hulls, would turn pale, translucent. After 10,000 years, they would not look like us. They would look like the greys of alien folklore. But the biggest change would be the mind. Living in a confined metal box, surrounded by absolute death, requires a different psychology. Agoraphobia, fear of open spaces, would become a survival trait. To a spacer, An open field on Earth would be terrifying. The blue sky would look like a gaping wound. They would crave the safety of walls. Their concept of individualism might vanish. On a spaceship, if one person makes a mistake, everyone dies. Dissent is dangerous. They might evolve into a hive mind, highly conformist, highly regimented. So, when the ship finally lands, it is not Homo sapiens that steps off the ramp. It is Homo spacians. And if they met us, if we somehow met our own descendants, we would look at them with horror, and they would look at us with disgust. We would be the hairy, heavy, violent apes of the gravity well. They would be the fragile, cold, calculating ghosts of the void. The distance between the stars doesn't just separate us in space, it separates us in species. The universe forces us to change, to survive it. It demands that we leave our humanity at the door. So, we have three choices: stay on Earth and eventually die when the sun expands, leave and lose our humanity in the process, or change the definition of human. What if we don't send bodies? What if we send ghosts? What if we leave the meat behind entirely? We need to talk about von Neumann probes, and we need to talk about uploading. Biology is expensive. It needs air. It needs water. It needs gravity. It is emotional. It dies easily. If the goal is simply to explore the galaxy, to touch the stars, then humans are the wrong tool for the job. We are too heavy. We are too fragile. So, let's stop sending astronauts. Let's send a seed. In the 1940 seconds, the mathematician John von Neumann proposed a terrifying concept: a machine that can reproduce itself. Imagine we build a robotic probe. It doesn't need life support. It doesn't need to come back. We launch it to a nearby star system. It lands on an asteroid. It mines the metal. It smelts the ore. It builds a factory. And then it builds a copy of itself. Actually, it builds two copies. These two new probes launch to two other stars. They land, they mine, they build, they launch 4 probes, then 8, then 16. This is exponential growth. It is a virus made of metal. Even if these ships travel slowly, say 1% the speed of light, the math is staggering. In a few million years, a blink of an eye, in cosmic time, this swarm of machines would visit every single star in the Milky Way galaxy. They would not just explore, they would consume. They would turn moons into factories. They would turn asteroids into fuel. They would be a wave of grey metal spreading through the dark. This is the von Neumann probe. It solves the problem of distance by ignoring time. The machine doesn't care if the trip takes 10,000 years. It can sleep. It can repair itself. It doesn't get lonely. But this solution creates a new horror. If it is possible for us to build these machines, then it should have been possible for others to build them billions of years ago. The galaxy is 13 billion years old. There has been plenty of time for a von Neumann swarm to eat the Milky Way 10 times over. So, where are they? If the galaxy is efficient, we should see them. We should see stars disappearing as they are dismantled for parts. We should see infrared heat from their engines. We should see the grey goo consuming the spiral arms. But we see nothing. The galaxy is pristine. The asteroids are untouched. This brings us back to the Great Filter. Maybe civilizations never reach this level. Maybe they destroy themselves before they can launch the first probe. Or maybe there is a code of conduct. Maybe advanced civilizations know that von Neumann probes are dangerous, because a self-replicating machine is just one mutation away from becoming a cancer. If a single line of code errors, if the command "stop reproducing" after 10 copies gets deleted, the machine will never stop. It will eat the entire universe. So, perhaps the galaxy is silent because everyone is afraid to light the match. But we humans, we are reckless. We are already talking about building self-replicating 3D printers for Mars. We might be the ones to unleash the plague. And if we do, our legacy will not be biological. It will be mechanical. Long after Earth is gone, The machines will still be out there, mining, building, launching, a clockwork empire. With no one left to read the time, the body is a cage. It anchors us to gravity. It limits our lifespan to a measly 80 years. It is made of heavy atoms that resist acceleration, but the mind is information, and information is weightless. If we can strip the mind away from the meat, if we can map the connectome of the brain and turn it into data, then we can achieve the ultimate speed. We can travel at the speed of light, not in a ship, but as a signal, mind uploading. Imagine a future where we don't build starships, we build receivers. We send a small, automated probe to Proxima Centauri. It takes 73,000 years to get there. It lands. It builds a supercomputer. It builds a robotic body. And it points a high-gain antenna back at Earth. On Earth, you step into a scanner. The laser maps your neurons. It digitizes your memories. It converts you into a stream of binary code. And then, we beam you. We fire a laser at the star. Your consciousness rides the beam. You travel through the void as pure light. No mass, no time. For you, the journey is instant. One moment you are in the scanner on Earth. The next moment, you open the eyes of your robotic avatar on Proxima Centauri. You have crossed the abyss in 4.2 years, but you didn't feel a second of it. This seems like the perfect escape, but it leads to a philosophical nightmare. The teleportation paradox. When the scanner scans you, does it move you, or does it copy you? If the scanner is non-destructive, then the original you is still on Earth. You step out of the machine, you go home, you live your life. Meanwhile, the copy you wakes up on Proxima Centauri. You are now two people, living two different lives, separated by a void that neither can cross. But if the scanner is destructive, if it has to slice your brain to map it, then you die on Earth, and a new person wakes up on the other side. That new person thinks they are you. They have your memories. They remember stepping into the scanner. They remember the love for your family. But are they you, or are they just a ghost haunting a machine? And consider the fragility of the signal. You are a beam of light traveling through 4 light years of dust and interference. What if a cloud of gas blocks the beam for a second? Do you lose a memory? Do you lose your childhood? Do you arrive lobotomized? What if the signal is corrupted? Do you wake up insane? And once you are there, you are trapped in the machine. You are dependent on the hardware. If the power fails, you vanish, and you can never come back, because to come back, you would have to beam yourself to Earth, and the Earth you would have to die to make room. We would become a species of scattered data packets, jumping from server to server, immortal, fast, but disconnected from the physical world. We would conquer the stars by giving up our souls. But maybe we don't need to send a whole mind. Maybe we don't need to colonize. Maybe we just need to look. And to look, we don't need a heavy ship. We need a kite. We have tried to send giant ships, too slow. We have tried to send machines, too dangerous. We have tried to send minds, too philosophical. So let's try something smaller. Let's try a chip. This is not science fiction. This is a real project happening right now. It is called Breakthrough Starshot. The idea is simple. Mass is the enemy. The lighter you are, the easier it is to accelerate. So, instead of a massive engine, we leave the engine on Earth. We build a massive field of lasers, gigawatts of power, and we build a spacecraft that weighs less than a gram, a tiny microchip attached to a sail, a light sail. We launch the chip into orbit. We aim the lasers, and we fire. The pressure of the light hitting the sail is tiny, but the chip is so light that it accelerates at 10,000 Gs. In just a few minutes, it reaches 20% the speed of light, 60,000 kilometers per second. At this speed, we can reach Mars in an hour. We can reach Pluto in a day. And we can reach Proxima Centauri in 20 years. 20 years. That is a human lifetime. A scientist could launch a probe and be alive to see the photos come back. This is our best hope. The only technology that can bridge the gap in our lifetime. But there is a catch, a heartbreaking catch. The Starshot probe is moving at 20% the speed of light. It has no engine, it has no brakes. It cannot stop. It travels for 20 years through the dark. It approaches the alien star system. The target planet looms large. It flies past the planet in minutes. It has perhaps 1 hour of useful observation time. It snaps photos frantically. It measures the magnetic field. It tastes the dust. And then it screams past. It shoots out the other side of the system, back into the eternal dark. It can never turn around. It can never go back. It becomes a piece of space junk, drifting forever between the stars. We are throwing seeds into the wind, thousands of them, hoping that one of them survives the dust collisions, hoping that one of them points its camera in the right direction. And then we wait. The probe takes the picture, but it has a tiny transmitter. It sends the data back to Earth. The signal travels at the speed of light. It takes another 4.24 years to get home, so we wait 24 years for a blurry picture of a world we can never visit. This is the reality of the Starshot. It is a drive-by shooting of knowledge. It emphasizes our helplessness. We can look, we can throw rocks, but we cannot stay. But even this tiny chip is a miracle. It is the first time humanity has ever reached out and touched something outside our prison cell. It is a scratch on the wall. But what if the prison isn't just distance? What if the prison is biology? What if the reason we feel trapped is because we are trying to force a biological timeline onto a geological universe? What if we could live forever? If you live for 1 billion years, a 73,000-year journey is just a commute. We need to talk about immortality and how it changes the map. The speed of light is only slow because our lives are short. To a mayfly, which lives for only 24 hours, a walk to the grocery store is a generational journey. It takes a lifetime. To a mountain, which lives for millions of years, the rise and fall of the Roman Empire is a split second. Speed is relative to lifespan. The reason 73,000 years to Proxima Centauri sounds like a prison sentence is because we die in 80 years. But what if we didn't? What if we solved the problem of aging? Biologists are beginning to view aging not as an inevitability, but as a disease. A genetic error that can be patched, telomeres can be lengthened, cells can be repaired. Imagine a future where humans are biologically immortal. We don't die of old age, we only die of accidents. If you live for 10,000 years, a 100-year trip to another star is not a life sentence. It is a long weekend. If you live for 1 million years, a trip across the galaxy is just a gap year. If we achieve immortality, the prison of speed dissolves. The bars melt away. We don't need warp drives. We don't need wormholes. We just need patience. We could drift between the stars at leisurely speeds, reading libraries of books, learning every instrument, watching the nebula pass by like scenery on a slow train. But immortality brings a new kind of prison, the prison of memory. The human brain has a storage limit. We are not designed to remember 10,000 years of history. To live that long, you would have to delete things. You would have to forget your childhood to make room for your adulthood. You would forget your first wife to make room for your 100th. You would become a ship of Theseus, constantly replacing your memories until there is nothing left of the original person who left Earth. And then there is boredom. Boredom is dangerous. In a finite life, boredom is a signal to do something new. But in an infinite life, on a spaceship drifting through the void for millennia, boredom becomes a psychosis. How many times can you read Hamlet? How many times can you simulate a beach in VR? After a few centuries, the immortal crew might retreat into their own minds. They might turn off the sensors. They might stop caring about the destination. They would become lotus eaters, drifting in a state of apathy, timeless and purposeless. And while they drift, the universe changes. The stars they are traveling to are not immortal. While the crew lives forever, the lights go out. Energy is life. Right now, we live in the stelliferous era, the age of stars. Energy is free. It pours down from the sky. We just have to put out a solar panel and catch it. But stars run out of fuel. Our sun has about 5 billion years left. Red dwarfs have trillions, but eventually they all die. They turn into white dwarfs, neutron stars, or black holes. The lights will go out. If humanity, or our post-human descendants, survives the journey, if we colonize the galaxy, we will eventually face an energy crisis of cosmic proportions. How do you run a civilization when the stars are dead? You turn to the monsters. Black holes. We usually think of them as destroyers, but they are also the most efficient batteries in the universe. When matter falls into a black hole, it speeds up. It creates an accretion disk. This disk gets so hot that it shines brighter than 1,000 suns. We can harvest that light. We can build a Dyson swarm not around a star, but around a black hole. But there is an even better way. The Penrose process. A spinning black hole drags space-time around with it. This region is called the ergosphere. If you drop a piece of mass into the ergosphere and break it in half, you can kick one half into the black hole and the other half will be flung out. And here is the magic. The piece that is flung out has more energy than the original piece you dropped in. You are stealing energy from the rotation of the black hole itself. You are slowing down the monster to power your toaster. A civilization living around a spinning supermassive black hole could survive for quintillions of years, long after the last star has faded to black. Imagine these cities, built on rings orbiting the event horizon. The sky is black, except for the terrifying, glowing eye of the hole. They would huddle around the fire of gravity, keeping warm in a dying universe. They would look at the ancient star charts and see a universe that used to be full of light. And they would wonder what it was like to live in the golden age of the 21st century. But even black holes are not eternal. They evaporate. Hawking radiation bleeds them dry. One by one, the black holes will shrink and explode. And then, there will be truly nothing. The expansion of the universe, Part 4, has a final cruel consequence. It cools everything down. As space expands, it stretches the wavelengths of photons. High energy becomes low energy. Visible light becomes infrared. Infrared becomes radio. Radio becomes silence. The universe is getting colder. We are heading toward absolute zero. This is the heat death, or the big freeze. It is the ultimate prison. Not a prison of walls, but a prison of entropy. Entropy states that order always turns into disorder. Energy always spreads out. Eventually, the universe will reach a state of maximum entropy. No heat can flow. No work can be done. No thought can be thought. Time itself will cease to have meaning, because time is just a measure of change, and in the heat death, nothing changes. Let's trace the timeline of the end. 100 trillion years from now, the last star is born. It is a tiny, dim red dwarf. It burns for a while, and then it dies. The universe goes dark. The only light comes from the faint glow of cooling white dwarfs and the accretion disks of black holes. 10, 15 years. The planets are detached from their orbits. Solar systems dissolve. Matter is lonely. 10, 40 years. Protons decay, hypothetically. The very matter that makes up our bodies, our ships, our cities, simply dissolves. The atoms unzip. 10, 100 years. The era of black holes ends. The last supermassive black hole evaporates in a flash of Hawking radiation. After that, just photons. Cooling, stretching, fading into the dark. This is the destiny of the cosmos. And it makes our current struggles seem small. It makes our prison of speed seem like a mercy. Because right now, we have places to go. We have stars to see. We have a universe that is alive and vibrant and burning with energy. We are complaining that it takes too long to get to the party, but we should be grateful that the party is still happening, because the doors are closing, the music is fading. We are the children of the dawn. We are living in the brief, bright flash of the universe's morning. So, is this it? Is this the end of the story? Or is there one final escape hatch? If we cannot escape space, and we cannot escape time, can we escape the universe itself? If the ship is sinking, do we have a lifeboat? We need to talk about the multiverse again, but not as a theory, as a destination. We need to talk about level 4 civilizations and the art of leaving the building. The universe is a sinking ship. We know this now. We know about the heat death. We know about the big freeze. We know that eventually the expansion will tear the galaxies apart and the stars will fade. Staying here is suicide. If humanity, or our AI descendants, survives for millions of years, eventually we will have to face the ultimate eviction notice. We have tried to cross the distance. We have tried to cheat time, but all those solutions kept us inside the box. Now we must ask, can we leave the box? If the speed of light is the speed limit of this universe, maybe we need to find a universe with a higher speed limit. This brings us to multiverse theory. We usually treat the multiverse as a mathematical curiosity, but for a Type 3 or Type 4 civilization facing the end of time, it is a survival plan. Theoretical physics suggests that our universe might be just one bubble in a boiling ocean of eternal inflation. If this is true, then outside our bubble, there are other universes, younger universes, hotter universes, universes where the stars are just turning on. How do we get there? We cannot fly through the void between universes. That void is expanding faster than light. We need a bridge, and the only object in our universe that punches a hole in space-time is a black hole. Some physicists, like Lee Smolin, have suggested that the singularity of a black hole is actually the seed of a new Big Bang. When matter is crushed out of our reality, it might be popping out into a new reality on the other side. Could we use this? Could we build a ship capable of surviving the journey into the singularity? The tidal forces would rip any material to atoms. The gravity would crush space and time into a point. It seems impossible. But maybe we don't need to send matter. Maybe we just need to send information. Recall the von Neumann probe, part 12. Recall mind uploading, part 13. If we could encode the sum total of human knowledge, culture, and consciousness into a stream of data, and if we could encode that data into the spin of particles falling into a black hole, maybe we could seed the new universe. We wouldn't survive as bodies. We would survive as a message, a genetic code for a new civilization. We would be throwing a bottle into the ultimate ocean, hoping that on the other side of the singularity, someone or something will find it. But this is a gamble. We don't know if the other side is habitable. We don't know if the laws of physics there allow for life. It might be a universe of pure radiation, or a universe with 10 dimensions where atoms cannot form. So, relying on accidental wormholes is risky. If we want to ensure our survival, we shouldn't look for a door, we should build one. We shouldn't look for a new universe. We should make one. To escape the heat death, we must become gods. In 1981, physicist Alan Guth proposed the theory of inflation. It explains how our universe grew from the size of a proton to the size of a grapefruit in a fraction of a second. It requires a specific state of matter, a false vacuum, high energy density, negative pressure. If you can create a false vacuum, space must expand. It must create a new Big Bang. Theoretical physicists have calculated that it might be possible to trigger this in a laboratory. We would need a particle accelerator far more powerful than the Large Hadron Collider. We would need to smash particles together with such violence that they create a microscopic region of false vacuum. If we do it right, that region will inflate. But it won't inflate into our lab. It won't destroy the Earth, because space-time is curved. the new universe would bud off from ours. It would pinch off. Imagine blowing a bubble inside a bubble, and then the inner bubble detaches and floats away. We would have created a baby universe. Inside that baby universe, there would be a new Big Bang, new stars, new galaxies, a fresh timeline with zero entropy. This is the ultimate escape. We build a station around the Genesis machine. We encode our DNA, our history, our minds into a capsule, and we drop it into the baby universe just before it pinches off. We plant the seed of humanity in a fresh garden, but here is the tragedy. The moment the baby universe detaches, it is gone. It disconnects from our space-time. There is no wormhole back. There is no phone line. We, the creators, stay behind. We stay in the dying universe. We stay with the freezing stars and the black holes. We become the parents who send their child away on a lifeboat, while they stay on the sinking ship. We will never know if it worked. We will never see the new stars. We will never meet the civilization that grows from our seed. They will grow up in a bright, warm universe. They might look at their history books, which tell of a great ancestor from a universe that passed away. They might worship us, or they might think we are a myth. And we will watch the lights go out. We will have the satisfaction of knowing that life continues, that consciousness continues, that the story didn't end with us. But we don't get to go. This brings us back to the stark reality of our situation. The multiverse is theoretical. Baby universes are speculative. Warp drives are impossible. The most likely scenario, the overwhelming probability, is that this is it. There is no escape. The speed of light is absolute. The distance is real. The end is coming. So, how do we live with that? How do we wake up in the morning, knowing we are trapped in a prison that is slowly freezing over? We need to change our perspective. We need to stop looking at the bars and start looking at the cell. We have spent this entire journey fighting the speed of light. We have called it a prison, a cage, a tragedy. We have lamented the fact that we cannot visit Andromeda. We have mourned the fact that we cannot speak to aliens. But let us pause. Let us look at the prison from a different angle. What if the speed of light is not a wall? What if it is a shield? Imagine a universe without a speed limit. Imagine if gravity and light traveled instantly. Every star in the universe would interact with every other star instantly. The gravity of 1 trillion galaxies would tug on our solar system simultaneously. Orbits would be chaotic. Planets would be ripped apart. The night sky would not be dark. It would be blindingly white, filled with the instant light of infinite stars. We would be fried by radiation from quasars, billions of light years away. The prison of speed is the only reason we exist. It isolates us. It buffers us. It creates a quiet, stable pocket of causality where evolution can happen in peace. We are safe because we are lonely. And what about the distance? Yes, Proxima Centauri is 73,000 years away. Yes, we may never leave this solar system. But look at what we have here. We have a planet with liquid water. We have an atmosphere that shields us. We have a moon that stabilizes our tilt. We have a sun that burns steady and slow. By realizing how unreachable the rest of the universe is, we realize how incredibly precious Earth is. There is no planet B waiting for us a warp jump away. There is no evacuation fleet coming from the stars. This rock is all we have. The isolation forces us to focus. It forces us to value the here and the now. We are travelers on a single ship, drifting through a void that is mostly dead. The fact that we are here, breathing, thinking, loving, is a statistical miracle. The speed of light forces us to be present. We cannot live in the future. We cannot live in Andromeda. We can only live here. So, tonight, go outside, look up at the stars. Don't look at them with frustration. Don't look at them as places you will never go. Look at them as the lights of other houses, far across a dark ocean. Know that there might be others out there, looking back at our sun, feeling the same isolation, feeling the same longing. We cannot touch hands. We cannot speak. But we can share the moment. We can share the knowledge that for a brief, shining instant, In the middle of the cold dark, we were awake. We saw the universe. We measured it. We understood its limits. And we accepted them. We are the prisoners of speed, but we are also the keepers of the light. And as long as we are here, the universe is not dark.